This is the lab report for Lab 6 for Physics 2212. So, getting started, the purpose of this lab was to explore Faraday's law by observing and computing the behavior of a magnet dropping down a conductive tube, in this case an aluminum foil roll, and forming an induced field. We'll see that the results are that for the experiment was 1.79 seconds, and for the computer model it was 1.938 seconds. In order to determine our different models, we used a couple fundamental principles. One, of course, being Faraday's law, which you can see on the right, which relates the EMF to the derivative of the magnetic flux, and the Biot-Savart law, which tells us the direction of the induced current, including and additionally Ohm's law and Newton's third law. The setup for our experiment was a bar magnet, a roll of aluminum foil, and a timer. Essentially, we were recording the time it took for the bar magnet to fall from the top to the bottom of the aluminum foil using the timer. And of course, we took this data several times and found the average to ensure that it was more accurate. Here you can see all of our data from experiment 1, and while our numbers were kind of all over the place, we ended up getting an average time of 1.79 seconds. The initial conditions for our computer model was what we set up next after finishing the experiment, as we found the tube length, tube radius, and the mass of the magnet in experiment 1. Here you can see that the tube length was 0.3 meters, and the radius was 0.028 meters, and the mass of the magnet was 0.035 kilograms. The magnetic dipole moment of 4.4016 comes from a previous lab that we did, so it was also found experimentally. On the right, you can see the final result of our computer model, which is, of course, including the image of the magnet and the solenoid, and then the graph of the time versus velocity of the magnet as it falls through the tube. It's important to note that in this model, we ignored air resistance, and we only focused on gravity and magnetic force. And again, as I stated earlier, the magnetic dipole moment was based on previously found values. Here are the most important parts of my GlowScript code, which of course includes the inputting of the initial values and then also calculating the magnetic field, magnetic dipole moment, magnetic flux, the magnetic force, and the total force. So, like I stated earlier, our experimental time, or the time found during the experiment, was 1.79 seconds. However, the computer model found the final time to be 1.938 seconds. This is a pretty close number, but it's important to look at a couple different reasons why there might be differences. Of course, in the computer model, we ignored air resistance, and in the experiment, it was very apparent. And in the computer model, we only focused on gravity and the magnetic force, which can be challenging, as in reality, like the experiment, there can be electrical and magnetic currents forming around us and creating these fields. And like I said, the magnetic dipole moment was based on previously found values in another experiment, so of course, depending on how accurate that experiment went, could be unhelpful to use. Further, the aluminum foil roll could have a non-uniform spread of the aluminum, and additionally, the magnet could hit the side of the wall of the aluminum roll and cause friction on its way down. And of course, as always, the human error, especially when it comes to timing. Here's a couple different things that we should look at. In the computer model, red is clockwise and blue is counterclockwise, which we know because the current above the magnet is counterclockwise and the current below the magnet is clockwise. And if we were to flip our magnet around, the induced current would be reversed. And as I was stating earlier with sources of error, the computational model could be considered more accurate, as there's no interfering electrical/magnetic fields, no friction with the foil, and no human error. And with that graph we saw earlier from the velocity versus time graph, the net force on the magnet decreases as its velocity increases until the upward magnetic force perfectly balances the constant downward gravitational force, which is when it reaches that plateau. If we had reduced the resistivity of the conductor close to zero, The magnetic would fall slower as, according to Ohm's law, the induced current would increase. And if there were holes in the tube, the magnet would fall faster because it would decrease the rings of current it would lose.